we're going to compute another line integral here, and this is just a different form of a line integral. We've got it written out as y squared dx plus x times dy, and although it looks a little different than what we're used to, there's really some work we have to do up front, which is we have to find the parametric form for our curve to replace, because x and y here are really all functions of t, the parameter. And that's going to depend on our particular curve that we're working on. And in this case, C is a line segment connecting a couple of points. We've got -5, -3, and 0, 2. So our first task is to come up with a parametric form for that line segment. This is not particularly challenging, but we may or may not remember how to do it. So I'm going to break it up into a couple of different pieces here. And we're just going to compute two linear functions, one for x, one for y. First, we'll find the slope by taking a look at the change in x as we go between the points. Again, we do this as terminal minus initial. So we have 0 minus -5. So the slope for the x component is 5. And for the y component, again, terminal minus initial. The difference there is 2 minus -3. And so its slope is also 5. So then we also need a point. And the way we set these up is by taking the initial point to represent the starting location. Kind of makes sense. So we know we have a slope of 5 in the x direction. So x of t is going to be 5t minus 5 using the x coordinate for the initial point there. And for the y component in our parametrization, again, we have a slope of 5, and we'll grab the initial point in the y, which is going to be -3. And I realized I got my subscript wrong, so let's fix that up. That should be a y sub 1. So now I've got the parametric curve, and what this does, it'll make a very specific kind of line segment. It's going to get from point A to point B over the time range 0 to 1 very specifically, and we can actually double check that. If I take t equals to 0, you'll see that when we put that in, we end up with -5, -3, and if I plug in t equals 1, I get our terminal point of 0 to 2. So when we're working with these particular line segments this way, we are getting a very specific range of values for t that will always map this out from 0 to 1. And that will, of course, play a role when I set up the limits for the integral. So now let's go ahead and set up that integral. And again, we've got our replacements for x and y. We're also going to need replacements for dx and dy. So if x is equal to 5t minus 5, then dx is going to be equal to 5 dt. And if y is equal to 5t minus 3, dy is going to be equal to 5 dt. So now I've got enough pieces that I can replace everything in our upper integral here in the problem statement with the parametric form for our curve. So now let's plug all of that in and set up our integral. Again, we're integrating from 0 to 1. That was all by design. And y is going to be equal to this 5t minus 3 times dx. Again, dx over here is 5 dt. So times 5 dt plus x. Again, x is 5t minus 5. And again, times dy, where dy is 5 dt. So there's the setup. Because we're integrating both of these with respect to t, I don't really need both of them. And in fact, we could even pull this common 5 out in front. Maybe we write this as the integral from 0 to 1 of 5t minus 3 plus 5t minus 5 dt. And then, of course, we can bring all this together. Make this the integral from 0 to 1, 10t minus 8 dt. And as far as integrals go in this class, This is a pretty easy one, so I will let you guys finish that off.